my research is obviously on precipitation extremes, but also on large-scale dynamics of the tropical atmosphere. So if you're interested in tropical dynamics, talk to me. So it's quite different from what Martin does. So yeah, I'm going to talk about precipitation extremes. I put up a reading that was recommended. Did anyone actually read that? Show of hands. Oh yeah, a few. That's good. Yes, so a lot of what I talk about is sort of expanded upon in that review paper by Paul O'Gorman. So I want to talk about the dynamics of precipitation extremes. And to motivate this, I'm going to show a couple of figures. Hopefully, Andrew King talked a little bit about this sort of stuff on Monday. But what I'm showing is some observations, an observational estimate of the sensitivity of precipitation extremes to the global mean temperature. So what has been done here, this is a paper by Seth Westra, is they've basically done a regression of precipitation extremes. So in this case, it's the annual maxima of daily precipitation. So I think that's one of the indices in that suite that you've been looking at. And they've looked at, across all stations across the world that they can find, what is the relationship in a regression sense. So when the global mean temperature increases, what happens to precipitation extremes? And this is the median result. And so what they estimate is that precipitation extremes on average, or in the median, increase by something like 7 or 8% for every Kelvin of global warming, for every degree centigrade of global warming. And then they wanted to know whether that was just a fluke. And so they went and scrambled the years associated with the global mean temperature. And so now you've sort of randomized everything, so you know there is no relationship. And then they calculated this same metric, and they get a distribution like this. It's centered on 0 because you know that if you scramble everything, you should get no relationship on average. But you get some relationships by randomness, by fluke. But the observed estimate is well outside this. So they kind of take this as evidence that there is indeed a real relationship between precipitation extremes and the global mean temperature. And you can look at models too. So this is a mean from CMIP5, and it's looking at that same index, the annual maximum of precipitation at every location. And again, it's trying to estimate how much do precipitation extremes change for every degree of change of global mean temperature. And this time it's a map, because with models you get a lot more data. And what you see is most of the world is blue, so that's an increase in precipitation extremes with warming, and it's in the same kind of range as what we saw in the observation. So it's kind of 6% on average, and there's some regions that are higher, some regions that are lower. There's some regions that are negative in these brown colors. But what is perhaps a bit surprising here is actually how well the models do, or how much they agree, at least. So from Martin's talk, you saw when you look at mean precipitation, so just the average precipitation annually or over a season, there's actually not many regions, especially on land, where the models agree on even the sign of the change in the future. And this is showing the stifling, so that's where most models agree on the sign, and it's actually almost everywhere. There's a few regions where there is no stifling, particularly in very arid regions where the precipitation extremes themselves will be pretty uncertain. But it gets this large-scale increase, and it even gets stifling on some of the regions of decrease. So we seem to have some confidence in this, at least in terms of model agreement. And so what I want to do is to kind of ask the question, why is that? Why would we expect precipitation extremes to increase with warming? Because just because the models agree doesn't mean they're necessarily right. And then I want to ask whether we can understand a little bit about this spatial pattern. So we see that, if I flick back again, there seems to be some agreement that in these subtropical ocean regions we have decreases in precipitation extremes, and everywhere else there's increases. Can we understand that? Whoops. And I haven't shown you yet, but we'll see that the actual magnitude varies quite a lot in different models. And so we want to understand what drives that and what would we need to do to try and reduce that uncertainty. Okay, so the first question is, what sets the precipitation rate? And we'll start with maybe the simplest, or the one you might think of first. What sets the global mean precipitation? Does anyone know how is the global mean precipitation rate determined? What is the physical process that actually determines how much rain we get on Earth globally? Sure, yes? Evaporation. Yep, and how do we know how much evaporation will happen? So Mike has just made the point that whatever comes down out of the sky must have got there somehow, so the global mean evaporation equals the global mean precipitation. So what determines the global mean evaporation? Yeah, so it's not actually temperature. It is how much the atmosphere cools radiatively. So if we look at a energy budget for the atmosphere, you have radiative fluxes from the surface, you have radiative fluxes at the top of the atmosphere, and it turns out there's a deficit. So the atmosphere, on average, is cooled by radiation. And then to balance that, you have the surface fluxes, the latent heat flux and the sensible heat flux. And it turns out on the global mean, the latent heat flux dominates. This is the evaporation. And so we know that whatever we're pumping into the atmosphere through evaporation must come down as precipitation. So this arrow is balanced exactly by precipitation in the global mean. And so it turns out that so it actually depends on the radiative fluxes. And those change because we add CO2 into the atmosphere, and those change because we warm the atmosphere. And so the atmosphere radiates in a different way. And it turns out that that increases at roughly 2 to 3% per Kelvin of global warming. And there's a bunch of papers that sort of describe that, but a nice reference is Alan Ingham. So that's the global mean, but that's actually very different from what happens to precipitation extremes. So in that picture I showed you, most of the rates of change were actually above 2 or 3%, and they were closer to 5, in some regions even 10%. So the global mean precipitation is actually not very relevant for this. So what about precipitation extremes? What kind of things might affect the strongest rain events that we get?
Temperature gradients.
Okay, temperature gradients where? Like horizontally or vertically? Okay, and how would they affect precipitation extremes?
They affect the strength of fronts and low pressure systems.
Yeah, so that is one thing that affects precipitation extremes. That's a very dynamical factor that affects precipitation extremes. But what about thermodynamic things? What happens when we just warm the atmosphere uniformly? What happens to the water vapor content, for instance? Yeah, that's right. So it increases. So that's one thing that can affect precipitation extremes. So the idea here, in a very rough sense, is that the heaviest rainfall that you get is somehow constrained by the available water vapor. So it's constrained by the water vapor in the column. And it turns out that increases very rapidly with temperature. So this is just a result of the relationship between saturation vapor pressure and temperature. And that increases at current temperatures at roughly 7% per Kelvin. And this should sound familiar from those the figure I showed at the start, which had a range of around 5 to 10%. So it's in that range. So this argument that somehow the amount of water vapor in the atmosphere constrains these heavy precipitation events. But what I want to do is to actually make this a bit more quantitative and think about this rather than just some amorphous, there's always water in the atmosphere that comes out. What are the actual dynamics that are behind this that drive precipitation extreme events? And so to do that, I'm going to use the board. So what we can consider is some sort of large-scale precipitation event. So we're thinking about something like daily precipitation on a grid box-sized area. So this will end up applying to models quite nicely. So if we think about a saturated air parcel, and it's moving through the atmosphere, and in particular it's rising, it's going to condense out water because it's cooling. And the rate at which it condenses out is written as C here. So C is the condensation. And it's proportional to the rate of change of the saturation specific humidity. That's QS. And so you can think of this as you go up in the atmosphere, the saturation specific humidity goes down. And so to keep the parcel at saturation, you've got to condense some of that water out. And it turns out this function, QS, is a thermodynamic function. So that means you can express it as, say, a function of temperature and pressure. So if you want to be a bit more explicit, this actually equals a function where epsilon is a constant, ES of T, so that's the saturation vapor pressure, so that is just a thermodynamic function of only temperature. And then it has this pressure term on the bottom. So it depends weakly on pressure. Mostly it depends on temperature. And so what we can also then therefore do is, instead of expressing this just in terms of temperature and pressure, we can actually express it in terms of a new variable, theta E star. So theta E star is the saturation equivalent potential temperature. So if people familiar with equivalent potential temperature? Hands? Okay, some of you. People familiar with potential temperature? Yeah, more of you. That's good. Okay, so So this is just a thermodynamic function itself. It's a function of temperature and pressure, so that means I can re-express this, no problem. And the reason we do this is because saturation equivalent potential temperature is conserved for adiabatic motions, including condensation. So if you think about a moist adiabat rising from or coming out from the surface, the saturation equivalent potential temperature along that moist adiabat will be constant. So that's the key reason we do this. Okay, and so let's go back to our parcel. We're thinking about this parcel rising. If it's a precipitation extreme event, we're assuming that there's a lot of condensation happening. So we can think about the thermodynamic equation. Minus. So I've just written, I don't know, can you see that at the back or is that too small? You can see it, okay. So this is the thermodynamic equation. So basically you have the temperature change is equal to, well, there's a temperature change, there's a amount of work that happens in the atmosphere, and then there's these heating terms. So the first heating term is condensation. And the second heating term is the radiative term. And the thing we're going to assume is that because we're in a precipitation extreme event, we've got lots of condensation, that this first term dominates. And so we can assume that the radiative terms or any other diabatic terms are small enough that we can neglect them. And so what that means is that we can assume that the rate of change of the equivalent potential temperature, the saturation equivalent potential temperature is 0. So we just think about an air parcel rising at saturation along the line of constant equivalent potential temperature. This is essentially just adiabatic rising of an air parcel. And then we can now think about what that means for the condensation rate. So with this assumption, I can now, using the chain rule, just write this as whoops. I can write that as two terms. So this is just simple chain rule. We have that QS is a function of two things, pressure and this saturation equivalent potential temperature. And so we just divide that into the two different derivatives. And so we have the rate of change of pressure times the derivative of saturation specific humidity with respect to pressure along this moist adiabat. And then we have the remaining term, which is the rate of change of saturation equivalent potential temperature. And this is the thing we assumed is 0. Ooh. Sorry. And so then we're just left with this one term, and that's what's the bottom equation on the screen. And so this is quite nice. So we have the condensation rate is proportional to dp dt. So this is how fast is pressure changing. And so we often consider this as a measure of the vertical velocity, which is often written as omega. So if you look in model output, there'll often be omega there, which is the vertical velocity in pressure coordinates, times this dqs dp along a moist adiabat. And this final thing is another thermodynamic function. And so that means we know what it does. We know what it does when temperature changes, and so we can think about how that affects precipitation extremes. And here it is. So the derivative of saturation humidity along moist adiabat is this thing. So that was the thing multiplying the omega, the vertical velocity. And it turns out it increases it as, with temperature in a similar way to the humidity itself, but not quite as rapidly. So this is a plot from paper by Paulo Gorman and Tapio Schneider, and they're showing the saturation specific humidity as a function of temperature. So we know that that increases at 6 or 7% per Kelvin. And then this is that gradient here, the dashed line. So it doesn't quite increase quite as fast, but it nonetheless increases with temperature. Okay, so we have a way of relating condensation to two things: the vertical motion in the atmosphere, as measured by the dP/dt, how fast pressure is changing, and this thermodynamic function, the derivative of saturation-specific humidity. And so then what we can say is, okay, for a precipitation extreme event, I'm going to assume that the precipitation is somehow related to the total amount of condensation we have. So we integrate that condensation in the vertical, so we get the whole column. And then we multiply that by epsilon, which is an efficiency, and we call that the precipitation. So this term in here is the column condensation. And then we just kind of put a fudge factor, if you like, of efficiency out the front. And so we can kind of treat this as a definition. And so then the efficiency sort of accounts for the fact that we're thinking about condensation, but we really want to think about precipitation. And so it's the conversion of all that condensed water into precipitation. So there's a lot of microphysical processes there. But it also accounts for these approximations that I've made to approximate the condensation rate. Okay, so why would we do this? Well, it turns out if you make some further assumptions, it actually gives you some real insight into the things that can affect precipitation extremes. So if we take this simple situation, suppose we have a vertical velocity profile. So this is the omega, the upward motion, that increases rapidly near the surface, is roughly constant for most of the troposphere, and then decreases near the tropopause. So you can think of this as you've got a bunch of air coming in near the surface and going out near the tropopause is some sort of very deep convective system. And so then we write down our precipitation again. There's a negative here. So that was the equation I had on the previous slide. So this is the efficiency, the condensation rate that I integrate in the vertical from the surface to the tropopause. And now we're assuming that omega is essentially constant in the whole troposphere except right near the surface and right at the tropopause, so we can actually take that out. And we'll just label it by its value at 500 hectopascals. So that's somewhere in the mid-troposphere. Oh, there's a clip. Cool. Oh, yeah. Brilliant. Thank you. But usually they have a thing you can tighten. Okay, so now we've reduced this just to an integral of that derivative of saturation-specific humidity. And we can make a further assumption that if the atmosphere is roughly along a moist adiabat, so that means the value of saturation equivalent potential temperature is roughly constant in the vertical, we can actually integrate this explicitly. And if you do this, you get the saturation-specific humidity near the surface minus the saturation-specific humidity near the tropopause, and the one at the tropopause is very small because there's hardly any water up there, so you will only end up with the one in the boundary layer. So that's this equation here. The precipitation during a precipitation extreme is proportional to three things: the efficiency, the pressure velocity, the vertical velocity in the mid-troposphere, and this saturation-specific humidity near the surface. And so that's really useful because we can say, okay, well, what happens when the climate changes? Well, the change in precipitation extremes is made up of three terms: a change in efficiency, a change in vertical velocity, and a change in the saturation-specific humidity near the surface. And that's very convenient because we can kind of think of those as three different processes. The first one being microphysical, because that was the efficiency with which the condensation became precipitation. So that's all about microphysical processes. The second one is dynamical. So that's what is the value of the pressure velocity in the mid-troposphere during these extreme events. It's all about the dynamics of precipitation extremes. And finally, thermodynamic, or thermodynamical as I've written it there. This is the change in saturation-specific humidity near the surface. And that we know is this 6 or 7% per Kelvin with warming associated with the change in saturation vapor pressure. Great. So this is really useful. If we think of the efficiency and the vertical velocity not changing, then precipitation extremes scale with that near-surface saturation specific humidity. This is about 7% per Kelvin, and this is what people call Clausius-Clapeyron scaling. So you can think about it as this idea that somehow the amount of water vapor constrains how much precipitation occurs, but if you go into the details of it, you can come up with this scaling by sort of making these approximations as to the condensation rate of a rising air parcel. Are there any questions about that? See some blank looks. Yes?
You're talking just about changing the saturation, but is there any changes in the vertical velocity?
Yes, so there are. So this is just sort of a null hypothesis you might think of. If nothing else changes, we'd expect 7% per Kelvin based on the approximations here. Yep, yeah.
Where did the G go in the integration?
Oh, sorry, yeah, the G should be here. I guess this is a proportionality sign. Yeah.
And just related to that, so in the O'Gorman paper, he talks about something very similar to this as a mass-weighted vertical integral throughout the column. Is that what that is?
Yes, so when you integrate in pressure, that's implicitly a mass weighting. And then the one on G comes from using that hydrostatic balance to get that. So it is an explicit mass weighting then. Okay, so the approximations I've just made, which are this very simple vertical velocity profile and the fact that the thermal structure is moist adiabatic, those actually aren't very good, particularly outside the tropics. So you can get away with this if you're thinking about a deep tropical system where the atmosphere is actually pretty close to moist adiabatic in the mean. But outside of that, this doesn't work too well. So it's kind of more of something that helps you think about how precipitation extremes change. And so what you're better off doing more generally is to just use those equations explicitly. So the equation for precipitation extremes that includes the full integral of the vertical velocity and the gradient of saturation specific humidity. And so we use this to construct a scaling and to try and understand what models are doing and why they might be uncertain in certain ways. And so in particular, what we can do first is say, well, let's assume this efficiency doesn't depend on space and time. We don't really have an a priori reason for doing that, but we'll see that it is not too bad an assumption, at least for model output. And so then what you get is that the precipitation extremes is just proportional to this integral of vertical velocity times a thermodynamic function. And so then the question is, okay, how well does this do? So this is from a recent paper by File, and they applied this scaling to CMIP5 models. And so this on the left, I think this is, so this is the annual maximum precipitation in the multimodal mean. So this is just what models are suggesting is the extreme, or the annual maximum precipitation in the current climate. And then the right is a calculation of that same statistic, but using the scaling. So instead of looking at the precipitation field, you actually look at omega, you look at this thermodynamic function, and you integrate it on days which the precipitation is very heavy. And the point is they kind of look the same. So this is the effect of ignoring that efficiency, and it turns out it's a pretty good assumption. So you can actually get most of the spatial structure. Largely you get the magnitude, although not quite. There's the precipitation extremes are a bit stronger in the actual simulated models rather than the scaling. But you do a pretty good job. So we can then use this to understand what's going on in models. So the other thing is that this scaling also explains changes in precipitation extremes across models. So this is back to a paper by Paul O'Gorman and Tapio Schneider in 2009. And what they're doing is comparing the scaling that I just showed you on the x-axis with what happens in different models to the simulated precipitation extremes. And so there's one plot for the extratropics, one for the tropics. And so on the y-axis you have how much do precipitation extremes in a given model increase per unit global warming, so per Kelvin of warming. And the x-axis is how does the scaling predict this. And so you see in both, apart from a couple of outliers, the models lie along this line. So that means the scaling is predicting what the model is doing in terms of precipitation extremes, both in the tropics and the extratropics. So if we can understand the scaling, we can understand why different models do different things. I guess the other thing to point out is that the values on the y-axis are from sort of 3 to 7 in the extratropics. So there is some variation between different models over what their increase in precipitation extremes are with warming. But those in the tropics go all the way from 0 to 30% per Kelvin. So some models are predicting this huge, huge increase in tropical precipitation extremes with warming. And so if you think about that, sort of 20 to 30% increase per unit global warming, if there's a 3 Kelvin warming, that's a doubling of the amount of rain you get in the once per year event. So that's a huge, huge change and has huge, huge implications if that's the case. Does anyone want to guess which two models that is? No, I better not say. I think it's the GFDL models. If there's ever an outlier in a plot, it's usually the GFDL model or the GIS model, or sometimes it's another model. Okay. All right, so the scaling's pretty complicated. It doesn't really give us a lot of insight immediately, but we can divide it into two components, a thermodynamic and a dynamic component. So this is, again, getting back to that very simple 3-term argument I had, but trying to keep some of the complexity. So the function that we are scaling the precipitation extremes with is this vertical velocity times thermodynamic function. And so we can divide the changes in that to a thermodynamic component where we only take into account the changes in the saturation humidity, and a dynamic component where we only take into account the changes in vertical velocity. And so there'll also be a cross term here that involves changes in both, but because the changes are relatively small, we generally expect that to be small, and so this approximation holds pretty well. So we can go ahead and look at how those dynamic and thermodynamic contributions work out in different models. So this is that same plot that I showed before, but now instead of the full scaling, just look at the solid symbols for the moment, don't worry about the open symbols. We're doing only a thermodynamic scaling. So we're only considering changes in the saturation-specific humidity, not changes in the dynamic component, that vertical velocity. And so what you see is that in the extratropics, everything lies roughly on the line. So that means that we can predict what a given model predicts for changes to extratropical precipitation extremes just by looking at how the temperature changes. Because that saturation-specific humidity is just a thermodynamic function, so we know what it does as a function of temperature. But things are very different in the tropics. So now there's firstly still those two outlier models that are way off the line, but even if you look at the remaining models, they don't really lie very close to the line. So that means that even if you know what happens to temperature, you know what happens to the thermodynamic part of the scaling, the dynamic changes are such that you don't actually know very accurately what the model will predict for precipitation extremes. So the dynamic changes are really important in the tropics. And I guess the other thing to note is, so if you look at the range over which the x and the y-axis is, the thermodynamic scaling is always between sort of 4 and 8% per Kelvin, because that depends on just this thermodynamic function, so we know roughly what that will do. But the dynamic changes can make that can change that to be a very wide range. Okay, so for those of you whose head is possibly spinning, what we've done here is constructed a simple scaling for precipitation extremes. And this says that there's sort of 3 different contributions to changes in precipitation extremes, microphysical, dynamic, and thermodynamic. And we can understand the thermodynamic part really well because that's just depending on the temperature. And we know that creates an increase in precipitation extremes at maybe 4 to 8% per Kelvin, depending on exactly where you are on the Earth, assuming there's no dynamic and microphysical changes. And then we can look at GCM projections and say, well, how true are some of these assumptions? What are the actual factors that, at least in models, give rise to these changes in precipitation extremes? And we find that the microphysical contributions are pretty small, at least for these daily extremes at the grid box scale. But the dynamic effects may be large, particularly in tropical regions. And the other thing is the GCMs disagree strongly on the dynamic contribution over the tropics as a whole. So while over the extratropics, that plot that I showed, everything kind of laid on the line for the thermodynamic scaling. So if we understand the changes in temperature, we understand the changes in precipitation extremes to some degree. In the tropics, that's not true at all. We don't know what happens to that vertical velocity, the omega. Are there any questions on that so far? You can feel free to talk, say you don't understand. Anything? Yes?
That's a nine question. So when you're scaling, like 3 slides back, can you comment on what explains the spread between the models you get there? So obviously the extremes, but just in the kind of the grouping of the models, what explains that spread?
So it's, so for the tropics, it's mostly what happens to omega on days of extreme precipitation. And so largely that's what is the distribution of vertical velocity in the tropics. And that differs a lot in different models, and the changes in that differs. I don't know, I can't sort of say why a particular model does a particular thing. And for the extratropics, it's, a lot of it is associated with the thermodynamic scaling, so it's sort of differences in how the temperature might change. So this scaling depends on the temperature on days of precipitation extremes. So the temperature change can be a little bit different to the actual mean temperature change if the days of extreme change a bit differently. Okay. So the other thing I wanted to talk a little bit about is this spatial pattern that we saw. So the at the start, I showed you this picture on the left. So that's the change in annual maximum precipitation among the different CMIP5 models in the multimodal mean. And then on the right is the scaling result. So this is using both the thermodynamic and dynamic components. And you see you actually get the spatial pattern as well using the scaling. So the scaling is useful for understanding that as well. And then here this paper has split this into the thermodynamic and dynamic components. So the term on the left is just changes in specific humidity or saturation-specific humidity. And this one on the right includes, or is only the changes in the vertical velocity component of the scaling. And so the point is this is pretty much one color. It's all blue. And it's just because as you warm the climate, the saturation-specific humidity increases a little bit. And so you get this sort of 5 to 6% per Kelvin, depending on where you are. And then the dynamic component is all different colors and has quite large changes in many regions. And some of them are decreases and some of them are increases. And this has to do with how does the vertical velocity on days of precipitation extremes change in the ensemble of models. And so I guess the point is that this spatial pattern determines what the spatial pattern of changes in precipitation extremes. So this is where these decreases in subtropical precipitation extremes happen, and why you have this very large increase near the equator in the Pacific, at least in the multimodal mean. And it's also so there are some dots, even though there's less stifling than in previous figures that I've shown you. There is some coherence across the models as to what happens to this dynamic component of precipitation extremes, particularly in these subtropical ocean regions where you have this reduction. And so why is that? Well, we actually don't know. So the current state is that we largely don't know, but there's a recent paper by Neil Tandon from the Canadian Met Service, I think, where they look at this, and the starting point they use is something called the quasi-geostrophic omega equation. So this is an equation used in mid-latitude dynamics to understand what happens to vertical motion. So it is basically a Laplacian on the left-hand side equals some forcing term. And so I don't want to get into the details of this equation, But essentially, their argument is that as the climate warms, the eddies associated with mid-latitude dynamics increase in size. And so this changes the horizontal Laplacian of the vertical velocity. And this is why you get these decreases in the subtropics. But that's pretty new work, so it's unclear whether it will, I guess, stand the test of time. Okay, and the final thing I wanted to talk about is precipitation extremes on a smaller scale. So mostly what I've been talking about so far is thinking about daily precipitation extremes on a model grid box, so 100 kilometers across or something. But that's not really how we observe precipitation extremes. We usually observe them through gauges, which are effectively point measurements. So this can be quite different to what you might expect from a GCM. And in particular, they're affected by small-scale convective processes. So if a big convective cloud forms over the gauge, you're going to get a huge amount of precipitation. If it's 10 kilometers to the east, you might get zero precipitation. And that's not going to be the case in a GCM grid box where you're averaging over a large enough area that you're averaging over an ensemble of clouds. Okay, so how do we understand these convective-scale precipitation extremes? Well, one way to look at this is actually to use observations. And so this is from a paper a few years ago, but a lot of other people have kind of picked up on this and done it for different regions. And what they've done is simply binned the precipitation in different temperature bins for a given location. So this is two locations, Hong Kong and the Netherlands, and the point of this paper was they could see it in different climate zones. So you've got kind of tropical and mid-latitude. And so for each bin, they calculate percentiles of the precipitation distribution. And so that's what the lines are. There's the 90th percentile in blue, the 99th in some other color, and the 99.9th in pink. And what they find is that for a given location, if you just look in variability in the current climate, the intensity of precipitation extremes increases as the temperature increases. And in particular, so the dashed lines here are now these theoretical curves to the extent that you can call them theoretical curves. The black lines are an increase of 7% per Kelvin, and the other colored lines are 14% per Kelvin. And so their point in this paper was that, well, sure, you do see this kind of Clausius-Clapeyron increase that people have been suggesting, but in fact, in certain temperature ranges, you can actually see a much more rapid increase of precipitation extremes with temperature. So they claim that it was 14% per Kelvin, a part of this range in the Netherlands, in Hong Kong, and you also to some degree see that in the Netherlands. And this made a bit of a splash, and people were sort of thinking about whether we can use these results to reason about global warming. So this is calculated just from variability. So when the atmosphere is warm, in the Netherlands, you're going to have a particular synoptic situation, and so you're going to have a particular type of dynamics, and that's a very different way of interpreting, a very different change than when you simply warm the globe uniformly. And so, a priori, it's not obvious whether you can whether this means anything for climate change, but that was kind of the argument that they were pushing. And so the question then was, well, what in terms of the framework I've been talking about, this kind of microphysical, dynamical, and thermodynamic changes to precipitation extremes, what could drive these so-called super Clausius-Clapeyron changes in convective-scale precipitation extremes? So if you have precipitation extremes increasing at 14% per Kelvin, you need more than just thermodynamic changes. You need either the vertical velocity to increase, or you need some changes to microphysics. And so there's been some sort of idealized work that has said, yeah, maybe the convective updraft velocity could increase. The efficiency also may depend on temperature. So one argument, which I actually made, not although I don't necessarily believe it, is that as the climate warms, more of the column becomes liquid as opposed to solid. So the freezing line, the freezing level gets lower, and liquid precipitation, rain, falls a lot faster than snow. And so this means that it spends less time in the atmosphere, and so it has less time to evaporate away. And so that can impact on the efficiency. So that's one sort of argument for why you might expect small-scale precipitation, convective precipitation extremes to have more of an effect from these kind of changes in updraft velocity and changes in efficiency. But the evidence is a bit mixed. So those studies I showed before were from cloud resolving simulations, but they're all very idealized. People have also looked at this over particular regions, so they do some simulations over, say, the southern UK, and they look at precipitation extremes in a historical period, and then they warm up the surface and say, okay, what happens when we increase temperature uniformly? And some have sort of said, yes, there's, you get this very rapid increase in precipitation extremes. It's faster than you'd expect from thermodynamic changes, and others do not find that, so it might depend on the region or the model. But I think it's sort of becoming clearer that you can't really use these observed scaling rates to translate directly to future changes, and that's a nice paper by Jiawei Bao, who's a PhD student at UNSW, who's shown that. Okay, I think that's all I have. So to kind of recap, precipitation extremes increase with warming, so both in simulations, and we have seen this in the observed record, at least when you aggregate enough regions together. But the rate of increase varies across models and across regions, and that's mostly because, at least on the large scale, because of this uncertain dynamical contribution. What is going to happen to the vertical velocity at the model grid scale when you get precipitation extremes? And so, if we want to constrain precipitation extremes and how they change with warming better, we really need to get a better handle on what constrains the vertical velocity field. So there's some work in this direction using the quasi-geostrophic omega equation, but that's only beginning. And I've talked a little bit about convective-scale precipitation extremes because there's a lot of other things you might want to think about there, including changes in efficiency, which, as far as we can tell, don't really affect the large scale as much. So I'll stop there and take questions.
Sorry, so I'm coming back to the same question. What are the observed changes, if there are any, in the large-scale vertical velocity field that people are already showing?
Yeah, so that's a very, very difficult thing to observe. Yeah, I mean, the only place you can get is reanalysis, but there it's essentially controlled by the model because it's, we're talking about very low values of, over a large region, the average vertical velocity would, a centimeter per second or something. So it's just not something you can observe directly. The best observation of it is the precipitation rate, because if it's precipitating hard, you need a strong vertical velocity. So it's kind of circular.
So don't they send on a daily basis from the same places for the last 30 years zones every day? Don't you get time series?
Yeah, so you get time series of temperature and humidity and horizontal winds, but you cannot get the vertical velocity from that. Yeah.
So when you started out deriving this scaling, you're assuming that C is approximately equal to minus dQs dt. If you swap QS with just Q, just specific humidity, and swap theta E star with just theta E, you derive similar scalings just for precipitation in general rather than extreme precipitation?
It becomes a little bit tricky because then you're sort of really just thinking vertical advection of water vapor in that case, right? But there's also these horizontal terms that will come in that may not be very small. Whereas the way I've set it up is that you're actually thinking about a parcel that's doing some adiabatic ascent. So it simplifies the problem a bit. In practice, it might work okay. I guess the reason you might not do that is that the water vapor it's not a thermodynamic function. So you require more information than just the temperature to get it. But yeah, you could try and derive it, but I think it becomes a bit more complicated because you have these other terms. Whereas when you kind of make this assumption that the air is just rising adiabatically, a lot of those other terms drop out, or you don't have to consider them. You kind of implicitly consider them with your adiabatic ascent.
So when you derive the models,
you kind of made an assumption that you can only use it in tropical areas. If that's right, or am I missing something? But then when you actually showed us the models in the graphs, you kind of did the whole globe.
Yes, so the comment about tropical areas was to this very simple scaling, which is this thing. So this is where I assumed that you had a certain structure of thermodynamic structure of the atmosphere, and you had a certain structure of the vertical velocity, and so that's how you derive this particular equation. But the way all the blue figures that I showed use this scaling, this equation 5, and so this includes the full dependence of omega on height. So whatever comes out of the model, if you're applying it to a model. So yeah, it seems to work pretty well over the globe, but you do require a lot of information. You need the whole profile of vertical velocity. Yep.
Can you use changes in the horizontal variables, so convergence and divergence, to look at the changes in the vertical velocity?
Yeah, so by mass continuity, there is an implied convergence and divergence, so they're kind of equivalent. If you could come up with a theory for the convergence and divergence, you'd have a theory for the vertical velocity. Does that answer your question?
Has that been done?
As far as I know, the main work is to use this quasi-geostrophic omega equation. So that applies in the extratropics more than the tropics. In terms of the tropics, I think it's a pretty open question. We know that the models aren't very good at getting that aspect because they differ so greatly from each other. Yes, so one way forward is to try and use observations to constrain it. So one, there was a paper published a few years ago where they took the sensitivity of tropical precipitation extremes to essentially El Nino, but interannual variations in temperature. Compared that to the sensitivity in models and found there was a relationship between the model sensitivity at interannual timescales and the model sensitivity to climate change. So it's kind of one of these emergent constraints. And so you could use that to constrain a little bit. Then that's limited by the accuracy of the observations, which it's quite hard on large scale to get good observations of precipitation extremes, and the extent to which you subscribe to this emergent constraint kind of framework.
Thank you, Marty.
Great.